Look at this commercial jet cruising at 30,000 feet. Navigating this high up in the atmosphere typically requires massive turbine engines and thousands of gallons of jet fuel to counter the freezing, hostile conditions. For humans to survive anywhere near this altitude, we require immense artificial life support. Climbers pushing toward the summit of Mount Everest rely entirely on heavy oxygen gear to keep their lungs functioning and their brains from shutting down. But right above those struggling climbers, a small flock of birds is navigating the exact same airspace without any external protection. While elite human athletes struggle for a single breath, these birds cross the Himalayas on pure muscle and instinct. Their journey originates down near sea level, in the peaceful, lush wetlands of Central Asia. Looking at them, the bar-headed goose appears completely unremarkable. They have a medium build, standard gray feathers, and no external features that suggest they are record-holding endurance athletes. This topographical map highlights their migration choices. Rather than taking a safe, low-altitude bypass around the mountains, the flock heads straight into the highest mountain range on Earth. Following this direct route means facing lethal threats. The elevation spikes violently along this path, exposing them to sudden, plunging sub-zero temperatures and a massive drop in air density. Choosing this antagonistic environment indicates that the bird's ordinary exterior hides an extraordinary, highly engineered internal system. The primary obstacle at this altitude is the lack of breathable air. At 30,000 feet, the atmosphere contains only a third of the oxygen found at sea level, a deficit that induces brain death and heart failure in most living creatures. This microscopic view shows how they survive. The goose utilizes a genetic mutation in its hemoglobin, the protein inside red blood cells that carries oxygen. These specific blood cells act like aggressive magnets, snatching and capturing the sparse oxygen molecules out of the thin air. Once captured, those oxygen molecules lock tightly into place. This genetic variation ensures the low-pressure atmosphere cannot strip the oxygen back out of the bloodstream. This oxygenated blood is delivered through a high density of capillaries in the flight muscles. This structural advantage allows the heart to maintain a steady, surgical stroke rate, instead of frantically overworking to compensate for thin air. This cardiovascular network functions as a high-performance engine designed for the thinnest fuel imaginable. But oxygen is only half the battle. The secondary threat is the paralyzing effect of extreme sub-zero temperatures and massive freezing headwinds. In this thermal imaging simulation, you can see how their brachimuscles act as literal biological furnaces. They burn immense amounts of energy during flight, solely to keep the bird from freezing solid mid-air. To optimize this biological hardware, the flock deploys a specific behavioral software, the Midnight Strategy. This side-by-side molecular comparison shows the physics of flying at night. By migrating after dark, they move through colder, denser air. Tightly packed cold air molecules increase aerodynamic lift under the wings, while providing more oxygen molecules per breath. The flock exploits these nighttime thermal physics to increase their lift, maximizing the efficiency of their biological machinery. This image captures the biological machine in action, the flock flying steadily forward, entirely unharmed and operating at peak efficiency. When you look at the jagged scale of the Himalayas in this wide shot, you realize the magnitude of the obstacle they just bypassed. Achieving this took millions of years of strict evolutionary iteration. We often view aerospace jets and pressurized oxygen tanks as the absolute pinnacle of mastering nature. The bar-headed goose provides a model of biological engineering that navigates the deadliest environment on Earth as a routine commute.